So MIC data is one of the most routinely collected and cheap forms of AMR data. Despite primarily being used in susceptibility testing of isolates, we believe that it could be, MIC distributions could be used to make greater inferences on AMR evolutionary dynamics. So by looking at differences in the MIC distributions of groups within a population, for example, different age groups, it may be possible to identify differences in transmission, infection, or selection. Performed at a local level, such as within a hospital or community, it may be, or it could improve the targeting of interventions and stewardship. So in a proof of concept study, we use datasets within the Vivli AMR register to demonstrate multinational MIC distribution variation by key grouping variables.
So the methods section, what we did was first of all extract the data. So we looked for the databases that had information on the MIC, but also sufficient metapopulation data that we could look at differences between subgroupings. We then developed an analysis. We had to think about the stages that you might go through in order to explore these differences. And we wrote our code. So that's an open source free software. And all of our code is available on a GitHub freely, but it's not yet developed into a user-friendly tool. What we did was to apply our flexible R code to the data that we had to try and extract insights about how MIC distributions might vary. So obviously a key question that we had to tackle was how to quantify MIC distribution differences. What we found was that if we plotted the data instead of this normal way of visualizing MIC distributions, instead as a cumulative distribution, we could see quite clearly the subgroup differences. For example, here on the x-axis, you've got the MIC values. On the y-axis, the cumulative proportion of isolates tested at these MIC values for different subgroupings, and you can clearly see that subgroup 5 is much more resistant strains than subgroup 1. To analyze this, we generated a novel index, which was the difference in the cumulative portion of isolates tested that were resistant or had the MIC value, and used an analysis of this index to look at differences within different bacteria and antibiotic combinations.
And in this graph here, we have the different MIC values on the x-axis and the cumulative proportion of isolates tested on the y-axis. And we have 3 different antibiotics: ampicillin, levofloxacin, and meropenem for E. coli and Staph aureus. And so for levofloxacin, we can see that there were clear age differences. And this inspired us to do a regression analysis to try and quantify what we were seeing visually. So the key takeaway from this is that we managed to identify that older age groups, so 65 and plus, had a higher odd of having a higher MIC than the age groups 19 to 64. Looking at infection sites and visualizing the data like this really managed to help us come up with some interesting questions. So, for example, why are bacteria from UTI samples in men more resistant? Or why are bacteria from gastro and blood samples more resistant?
We do believe that we have identified a new dimension for harnessing existing AMR data, and we can find no publications performing this analysis at a subnational level, which is a clear gap. We hope we have demonstrated that this method could be used to reveal hidden transmission sources and effective antibiotic use, producing actionable conclusions like optimizing interventions against resistant pathogens. This methodology is also very generalizable and could easily be applied to any setting with MIC data to look at any patient groups, which may be useful in low resource settings. We're therefore seeking to generate a user-friendly app using our open source code.